Hello guys, Mr. Gomes here. Just want to give you guys a little bit of introduction into the different things that affect the behavior of gases, the different variables. They're going to be pressure, volume, moles, temperature, things like that. Okay, so let's just go ahead and jump right into this. You're more than welcome to use the notes guide if you like, or just if you'd like to take any notes on your own, you're welcome to do that too. So let's first of all talk about temperature. Okay, what is temperature? Temperature, typically in English, we say, well, that's how hot or cold something is, which is fine. But a better scientific definition for it is the measurement of average kinetic energy. So the higher the temperature that something has, the more movement that the particles in that substance have. Okay, and conversely, the lower the temperature, the less movement. Okay, now that's on average. Okay, so for example, solids are the coldest. Okay, they have the lowest temperature, so they have the least amount of kinetic energy. Okay, which means they're in place. They shake and they move around, but they are not. They don't have like no movement whatsoever in place. They're vibrating in place, so they do have kinetic energy, but it's very low. Gases, on the other hand, are bouncing all over the place. Okay, so gases have the highest kinetic energy, and they're usually at the highest temperature of any substance. All right, so let's look here at helium. Okay, the number of particles. Okay, at a particular speed for a sample of helium. So you see here that at negative 100 degrees Celsius, okay, on average here, if I just take the peak as the average, which is not necessarily the case, but just to make a point, the coldest that it is, or let's say the hottest it gets, the more the average particle speed. So like 1,000, 1,500, 2,000, okay, meters per second. But notice that not every particle is at that exact speed. There is a range, okay? This actually looks a little bit like flattening the curve, doesn't it? With the coronavirus situation. But it's kind of the same idea. The lower the temperature here, the lower the average. Okay, so you have more chunked in at that lower average energy, as opposed to a higher temperature. You're gonna spread them out. The average is gonna be bigger there at a higher velocity. Okay, for average velocity for the molecules, or average kinetic energy. All right, so another thing here to think about is, what if you have different gases at the same temperature? Okay, so here's the thing. Kinetic energy equals 1/2 mass times velocity squared. So speed is a big factor, especially since it's squared. So speed has to do with kinetic energy a lot. But look at this, also mass. Okay, mass is also important when it comes to measuring kinetic energy. Okay, so for example, if all of these noble gases here, helium, neon, argon, krypton, and xenon, are at the same temperature, which means they're going to have the same kinetic energy. All of these have the same average kinetic energy because they're at the same temperature. They're at 100 degrees Celsius, okay? They still can have different speeds, okay? Because helium is the lightest. Okay, so since its M is small, its V is going to be big. So if you look at helium here with the dots, its average, okay, is going to be over here between 12 and 1,300, okay? As opposed to xenon, which is the heaviest of the noble gases listed here, okay? Its average here with the solid black line is significantly lower. So maybe around 250 meters per second, okay? Because its mass is bigger for xenon, its velocity will be lower. But when you multiply those together, xenon and helium right here have the same kinetic energy, average kinetic energy, I should say. All right, so to review here really quick about temperature. Temperature is average kinetic energy. When two gases are at the same temperature, they have the same kinetic energy. It does not mean that every single particle is moving at the same speed. Average is the key term, okay? And then kinetic energy equals 1/2 mv squared. Two gases at the same temperature will have the same kinetic energy, but different velocities because their masses are different. Lighter ones will be faster, heavier ones will be slower. All right, and I know I'm going through this really fast. I don't want to make this video very long. If you need to pause at any point and review something, please feel free to do so. So let's practice a little bit here, okay? So I have all these gases here at 25 degrees Celsius. So I have a mole of oxygen, a mole of CO2, 2 moles of CO2, and 1 mole of helium, okay? So which gas has the greatest kinetic energy? None. All the same. All of them are the same, okay? Because they're at the same temperature. Okay, so all have the same average kinetic energy. Which one has the greatest velocity? Well, that'll depend on mass, okay? The molar mass of oxygen is 16. Of CO2, it's around 44. Same thing here. And then helium, it's around 4. So helium is going to be the fastest, okay, because it's the lightest. All right. And then if we were to think about other things, like what about density? Okay, well, we've got the same volume here, but here we've got more mass, and here we've got even more mass, right? Because we've got 2 moles, so this would be the densest. Is that a word? The greatest density. I'm going to say it like that. This would have the greatest density. And then here we only have 4 grams. Remember, density is mass over volume, right? We've got 4 grams over the same volume here, which is the same for all of them. We could say it's like a liter or something, okay? So this would have the lowest density, okay? The least amount of mass per volume, okay? All right, so let's move on. Let's talk about temperature scale. So the Kelvin scale is a new scale. We talked a little bit about in the demo video. 0 Kelvin is absolute zero, the coldest temperature in the universe, okay, which is negative 273 Celsius, where all molecular motion stops. So we can convert between these using this formula right here. If I have 25 degrees Celsius, how many Kelvin is that? Well, 25 plus 273 is 298. Okay, so pause this video real quick, try these 3 problems, see if you can figure it out, and I'll write down the answer here in just a second. Okay, so here are the answers for these problems. Okay, 0 plus 273. This case here, we're going to do 400 minus 273, and we're going to get 127 Celsius. Both of these are in Kelvin. And then negative 100 Celsius plus 273 is 173 Kelvin. All right, so let's talk about pressure a little bit. Pressure is the amount of force that you exert on any given area. Okay, so the atmosphere exerts pressure on us all the time. Okay, we don't feel it because we've lived under this atmosphere from the moment that we were born. Okay, but there is a big weight of gases that is exerting pressure on you. How much pressure is that? It's 100,000 newtons per meter squared. That doesn't mean a whole lot to you, but that 100,000 newtons is about the weight of a large truck on a meter squared. So that would be 3 feet by 3 feet, so 9 feet squared. You have about the weight of a truck. Okay, so you're actually super strong. It's just that all of us, all humans, are super strong because we're carrying all this weight on us all the time from the atmosphere. Okay, now pressure depends on how often particles of a gas hit the surface and also the energy of those collisions. Okay, so the more collisions, the more pressure, and you observe that in the demo that we watched earlier, the demo video, okay? Because the more often that those gas particles hit something, say if they're in a container, the more that they hit that wall of that container, or the greater the collisions, the more force they're exerting, okay? So the more pressure. Same thing with the atmosphere. More gas collisions against you means more pressure. Less gas collisions or less energetic collisions, less pressure. All right, so pressure is caused by gas particles slamming into the container's walls. That's what we just talked about. Now here we're going to talk about units of pressure, okay? There are a gazillion units of pressure. Atmospheres is the current international scientific one, but throughout history there have been so many that have been used and they never really went away. Okay, So here, that was just to wake you up. Here are the conversion factors. 1 atmosphere equals 760 torr, which is the same thing as 760 millimeters of mercury, and 101.3 kilopascals. So I've got a couple practice problems so we can practice converting these real quick. So 789 torr equals how many atmospheres? So this is like any other unit conversion, okay? I have 760 torr equals 1 atmosphere. Okay, so 789 divided by 760, 1.04 atmospheres. My torrs canceled out. I rounded to 3 sig figs right there. All right, what if I'm going from 25 atmospheres to kilopascals? Well, 1 atmosphere I'm going to put down here so my units can cancel each other out. And then I'm going to do 101.3 kilopascals. Okay, 25 times 101.3 is 25, 32.5. But I only have 2 sig figs here. Okay, so that 3 is going to round down. And I'm going to put my 2 placeholder zeros here. So 2,500 kilopascals. Okay, so again, I'm going super fast because I don't want to bore you to death. If you need to go back and watch it again, please do so. All right, so just 2 other things I want to talk about real quick, and then we'll be done with this lecture, okay? So we also going to talk lots about volume and moles, okay? Volume is the amount of space that a gas or anything occupies, okay? For this unit, we're usually going to talk about liters or milliliters, okay? And remember, say if I have 100 mils, to convert that to liters, I go back 3 places. So 1, 2, 3. 0.100 or 0.1 liter is the same thing as 100 milliliters. Okay, that's it for volume. Moles, we talk lots about moles. You know what moles are. It's the amount of particles. Okay, the symbol that we're going to use for moles is N, as in number of moles. Okay, remember that lowercase m is for mass, uppercase M is for molarity. Okay, and one thing that we've talked about briefly in the past, but we're going to bring it back, is 1 mole of a gas at STP equals 22.4 liters. So STP is standard temperature and pressure. The standard temperature is 0 degrees Celsius and the standard pressure is 1 atmosphere. So if you get a gas at 0 degrees Celsius and 1 atmosphere, 1 mole of that gas will be 22.4 liters. Okay, and that is it for just the introduction of the different factors that affect the behavior of gases.